Okay, so I guess I'll start by reviewing what we discussed last time. So we've been discussing the Reisner-Nordstrom. I always forget and start on the wrong blackboard. We were discussing the Reisner-Nordstrom black hole. And in the standard coordinate system, we can write that as r minus r plus, the prefactor of dt squared goes to 0 at the inner and outer horizons r plus and r minus. And then the factor of front of dr squared is the inverse of that. Where for Reisner-Nordstrom, the inner and outer horizons are at r plus or minus is equal to m plus or minus the square root of m squared minus q squared. So when m is much bigger than q, this just looks like much like an ordinary Schwarzschild black hole, but something very special. When m is less than q, this becomes imaginary. So there aren't any horizons for any real value of the radius. And you can get all the way to the origin, where there's then a naked curvature singularity. OK, so we were especially interested in the so-called extreme case, or extremal Reisner-Nordstrom, for which m is equal to q, and r plus is equal to r minus. And in that case, we found that there is an infinitely long throat that, goes on forever, which develops. The proper distance at fixed time to the horizon becomes infinite. OK, that doesn't mean the horizon is infinitely far away. One of the many weird things that happens in general relativity, you can still fall across it in a finite amount of time, even though at any instant of time the distance is infinite. And also null geodesics get there in finite affine time. And we talked about a near horizon limit in which we wrote r equals m plus epsilon rho. So if we keep rho finite, or maybe I used lambda. What did I use? Lambda, maybe? I can't remember. But keep rho finite, do the coordinate transformation involving this. There was also a transformation on the time variable, which forced us into this near horizon region. And we found that the near horizon region was in the near horizon, near r equals m, we could write the metric as just ds squared over q squared, where q is the charge, is equal to minus d tau squared plus, after some coordinate transformations, plus dy squared over y squared plus d omega 2 squared, the so-called Robinson-Bertotti universe. And it is a product space of, I don't know how to draw a picture of ADS2, but ADS2, two-dimensional anti-de Sitter space times the two-sphere. So this is the simplest example of increasingly more complex and intricate near horizon limits that have been studied in physics. This was the first one. It was, I think it was the 60s. But there's a lot of interesting things to be thought about because it's like a fixed point. Going near the horizon's high redshift. It's like going to low energy in a condensed matter system. And there's critical behavior that occurs there that resembles in every detail the critical behavior that you've studied in other physics courses. And in fact, ultimately, by the end of the course, we'll see that it doesn't just resemble, it is the same thing in a different description. That is, general relativity is statistical is thermodynamics, at least in some circumstances. And the full generality in which that statement applies is something that people are trying to understand now, but we don't fully. But there are some very definite, incontrovertible examples, including, as we'll see in the coming weeks, some about which we may get actual astronomical measurements in the near future. We also talked about the symmetries, and in this fixed point at the bottom of the throat, there are extra killing symmetries. And what's a killing symmetry? So a killing symmetry, and we're going to come back to, in this lecture, to discuss more kinds of, even more symmetries. But a killing symmetry is where or a killing vector field. A killing vector field generates vector fields generate symmetries. They generate a motion along a manifold. And a killing vector field is a vector field with the property that its Lie derivative, which is zeta alpha d alpha g mu nu plus g mu alpha d nu zeta alpha plus g nu alpha d mu zeta alpha, which works out to be the symmetrized covariant derivative of zeta. And this is equal to 0 for a killing vector. And Reissner-Nordstrom has 4 or 3 rotations, spherical symmetry, and 1 time translation. And however, the Robinson-Bertozzi universe, which is this near horizon limit, if it's convenient to define t plus or minus equals tau plus or minus y, and then we have 3 killing vector fields, which we can write as d plus plus d minus. That's ordinary time translations. And then we have t plus d plus t minus d minus. And then we have t plus squared d plus t minus squared d minus. This is the conformal group in 1 dimension. And these are all isometries of the near horizon region. And in fact, I guess I'm getting in the habit of giving you little peeks into the future, but actually we'll see, probably not till next semester, that in fact this generalized to making this an arbitrary function of t plus or t minus, and that you then get a whole, actually a whole Virasoro symmetry that acts on this region. But for now, we're interested in these, which generate a group, and well, the Lie bracket algebra of these vector fields is the Lie algebra of SL2R, which is the same as the Lie algebra of SO21, which is like the Lorentz group in 2 plus 1 dimensions. And moreover, this is the infinitesimal action, but this is easily exponentiated to get the finite group action given a point t plus and t minus. If we do this, t minus goes to a t minus plus b over c t minus plus d. So it's easy to check that this is actually a symmetry of that ADS2 metric. And, every theoretical physicist has, I didn't assign it as a problem, but it's a good thing to do. Every theoretical physicist, at least in our field, has done this calculation at least 100 times. So it's an important fact that that thing is invariant under this. OK, so that is all. Oh, I guess just one more thing I want to say is that this is the Penrose diagram of ADS2. There are two boundaries. And this t plus or minus coordinates just cover a finite region of this. This would be the line where this is y equals infinity. This would be y equals 0. Y is going like 1 over r minus m. And but once you get into the ADS2 region, these boundaries are just phantoms. The complete geodesic extension of the geometry goes beyond those analytic completion of it, goes beyond these where the horizon was when this near horizon geometry is embedded. So the full asymptotically flat spacetime gets embedded like this. But once you take the near horizon limit and drop that factor, you can continue this geometry into the whole region. And maybe it's just worth drawing that again because it's an important picture. Looks like this. So here we have the singularity. Here's r equals m, r equals m. Here's r equals 0. And here's r equals infinity. And the ADS2 region is it sort of hugs this so if you map this strip over to here, this dashed line is what was the horizon in the full asymptotically flat region. So that is everything. That is the review of last time. Are there any questions about that? OK, great. So another topic which I will probably talk more about later, but I just want to allude to now, is because it is something, a purely classical phenomena, the so-called attractor mechanism. So it's this sort of curious thing. I mean, now we're beginning, or at least we have the impression that we're beginning to understand how to think about what a quantum black hole is. And the funny thing is that there were so many, just the equations of general relativity have of classical general relativity have so many kind of hints in them. There are funny things that happen in the equations that seem to have no real purpose until you realize that you couldn't have a successful quantum completion of the story if the classical equations didn't already have these seemingly peculiar properties. And one of those is the attractor mechanism. And that has to do with, well, you can already kind of see it here. So there's the near horizon region of the black hole is the surface of infinite redshift. And when you study renormalization group flows in condensed matter phenomena, you have fixed points like this. And the statement about the fixed point is that if you change something a little bit far, if you change where you start from, so this is some kind of parameter space, coupling constant space, you change the initial conditions where you started out by a little bit, and the change in what happens as you approach the fixed point gets very, very small, and you certainly end up at exactly the same place here. Now, that's for an this is what's called an attractive fixed point. There are also fixed points, a little harder to draw, which are not attractive. I mean, there's a whole zoo of different kinds of phenomena you can have, but these are two basic examples. So it might look like this. So in a diagram like this, in order to hit the fixed point, you have to tune the initial starting point with exponential precision. In general, if you mess up a little bit, you'll miss it. So of course there are lots of examples of quantum physical systems with this behavior, but this is sort of the simplest kind of example. And black holes appear to be in this class. And why exactly they always end up being in that class, we're not sure. It seems like it's hard to understand how the picture could be pieced together if they weren't in that class. And it's partly related to the formula I wrote down in the first lecture of the entropy of a black hole, which is they have this enormous entropy. And so if you want to increase the entropy, the black hole is always your best option. Now, what does it mean? What is the analog of this picture over here? Well, this was a solution of general relativity. But we could imagine changing this picture, and there are many, many examples of this. We could imagine changing this picture in different ways. We could add higher derivative terms to the action. We could add some scalar fields. We could add different kinds of charges. We could have scalar fields coupled to charges. There's all kinds of different things that could happen. And this is just at the level of solving classical equations. So we could, an example is suppose we add a scalar field phi. and then we couple it, we give it a Lagrange, we give it some equation of motion, and we might couple it to the electromagnetic field. So we might have a coupling of the form phi, or some power of phi, times the field strength squared. Some arbitrarily interacting coupled system. Now, I'm not going to try to make a completely general statement here, but what tends to happen is even in those situations, the scalar field will be driven to an attractive, again, you can start with different values of the scalar field at infinity, and the scalar field will be driven to an attractive fixed point down here, independently of how you start out here. So it really has the structure of a renormalization group flow that if you change things out here, the black hole has a life of its own. If you change things out here, you don't change them. The horizon is insensitive to that. And that aspect of the classical field equation is needed to be true in order for the black hole to have an interpretation as an independent statistical system. If you have an atom, it has some number of states and some number of orbits, and if you throw it into a glass of water, or you move it around, some basic properties of it won't change, and the same thing is true of a black hole. And we'll need to use this fact somewhat later when we start talking about black hole entropy, and I think it's better to write down equations for it at the time that we actually need it, rather than now. But I'm mentioning it because it's something that you see, a classical property of black holes. Any questions about that? Yeah.
Does matter have to satisfy some energy condition?
Yeah, matter will always have to satisfy an energy condition. If you don't have an energy condition, the vacuum's not stable. So when I say, and nothing makes any sense. And so when I say in generic theories, I mean generic well-behaved theories. Yeah. Okay. So the next thing I want to discuss, and you had a homework problem on this, is I think they're called isotropic coordinates. So if we write r equals rho plus q, then what happens? This prefactor, which is then r minus q squared or r minus q squared over r squared, which is the prefactor in front of the t squared, becomes rho squared over rho plus q squared. And so the metric becomes ds squared is equal to minus rho squared over rho plus q squared dt squared plus dr is equal to d rho plus d rho squared over rho squared times rho plus q squared plus rho plus q squared d omega squared. But I actually want to write all of this as rho plus q squared times d rho squared, rho plus q squared over rho squared times d rho squared plus rho squared d omega squared. And the reason I want to do that is that this is just dx squared. This is just the flat metric. So in these coordinates, the spatial metric is flat times a conformal factor, which is diverging at the horizon, which is rho equals 0. And so the whole, this whole thing now becomes equal to minus, which way did I write it? Minus 1 over v squared dt squared plus v squared dx squared. Now, where v is equal to rho plus q over rho, or 1 plus q over rho. Okay, so this, I think, gives you a little bit of a picture of the spatial geometry. So of how the spatial geometry changes. So when rho is large, v is approximately 1. So v is approximately 1 out here at rho is equals infinity. And then it starts to get important when you get near rho equals 0. And when you get to rho equals 0, this thing, v, we can think of v as just q over rho. So v squared is q squared over rho squared. And that 1 over rho squared will cancel this rho squared. So we just get down here at rho equals 0, it's infinitely far away. Down here, we just get a 2-sphere of radius q, something we already saw in the other metric. Now, the interesting thing about writing the metric in this form is it, in this particular form, of course, there are many different forms of the Riester-Nordstrom metric, which are useful for different purposes. But in this form, it turns out that if we replace, these are called the Papetru-Majumdar metrics, kind of an amazing thing. I might be misspelling this, I'm not sure. If we take v goes to 1 plus the sum over any number, let's say n, of qn, qk over x minus xk, you can show, and it's not that hard because this is a pretty simple form of the metric, you can show that this is still a solution, still an exact solution of the Einstein equation. So what does this solution look like? Well, now we have n singularities. And if we're far from any of the singularities, the metric is, of course, just flat. But whenever we get very near any of these xk's, we get this long tube forming. So we get a picture like this with a bunch of it's a multi-black hole solution. And the total charge is the sum of qk. And what is the total mass? Well, it's easy to read the total mass off this, because if you take x much greater than xk, so the mass is measured out at infinity, if you take x much greater than xk, to leading order, we can forget about the minus xk here, and this becomes the v that you would have just for an extreme Reissner-Nordstrom whose charge is the sum of qk and whose mass is equal to its charge, the sum of qk. Yeah. It's an exact static solution. So it's one of very few exact solutions of the Einstein equation with only one Killing vector. And so, okay, these people just studied it. They just, I would have planted that question if I could have, because it is really rather surprising when it was studied, discovered just by looking at the Einstein equation. You know, it's a big, complicated nonlinear equation. Why would you expect to have, you know, exact cancellation of so what happens here, the reason, you might say, why don't these black holes attract one another or repel? And well, obviously what's happening is that gravitational attraction, they all have the same charge, right? If you try to make one of these charges negative, you get into trouble. You have this goes through zero and you have a singularity. So they all have to be the same size. And so, okay, you say, all right, if I have two point-like objects, I can find a position where their attraction and repulsion exactly cancels. But general relativity is not Newtonian gravity. And the forces depend on distance. There's subleading corrections. So it's a very surprising thing a priori that you could arrange to have an arbitrary collection of n objects and have all of the forces cancel exactly. Now, so yes.
Is there any restriction on the xn or xk?
No.
There's no restriction.
There's no restriction. So it looks like a conspiracy, right? And I think the reason for this conspiracy wasn't really understood until the early 80s, and it's related to supersymmetry, which is what I'm about to explain. So that's another thing about gravity, is that so I'm going to talk about that today. It has a supersymmetric extension, and a lot of its properties that seem miraculous can only really be fully understood only understood in a satisfying way. I don't think there's any satisfying explanation other than do the math of why these things don't, you know, why they're always in perfect balance, why they should always be perfect balance. And what I'm going to show in a minute, or I'm not going to show all the details, but we know that in general relativity, again, there's something really strange, which I would also say, or is best understood by supersymmetry, is we take the total energy of any, you know, asymptotically flat solution of the Einstein equation, it's always positive. I mean, why should that be true? You know, it's a nonlinear equation. The terms have arbitrary, you know, signs. I mean, why couldn't you have, you know, there's negative gravitational potential energy. Why couldn't you put some gravitons close to one another and have that, it's completely inobvious, yet true, that the mass is always greater than 0. But you can, if you have the Einstein-Maxwell equation, which is what we're solving here, there's an even stronger bound that the mass is greater than or equal to the charge. And these solutions saturate that bound. You see, they have the mass exactly equal to the charge. And so you can't go any lower in energy. If there were any attraction or repulsion, it would mean that you could lower the energy by moving them either closer or farther apart, thereby violating this bound. So it's the fact that these spacetimes saturate a bound that they're stable. It's the same reason they're stable under small perturbations. It's the same reason, well, it's a more complicated version of the reason that the vacuum is stable. So my next thing is, I previously when I've taught courses on black holes, I haven't mentioned anything about supersymmetry, but I realize that I sort of secretly think about it all the time when I'm thinking about properties of black holes, and so I should try to say a little bit about it. I'm going to go on and do that now, but let me just pause for questions. Okay. Yeah. The individual Q's can be arbitrary, right? You can also think about the following here. This picture, if you can take two of the x's to become very close. So each one of these regions here, at the bottom of each of these throats, I have an AdS2 times S2. But I can if I want, if I take the x's close, and what do I mean by close? I mean, suppose I take x17 minus x18 to be much less than Q7, the size of Q17 or Q18. So I get something like this, where I have a throat, goes on for a long time, and I get into an AdS2 times S2 region, which then splits into two throats. So it doesn't always look exactly like that if you take them very close together. And the study of the structure of these multi-Reisner-Nordstrom solutions has a lot of interesting physics in it. Okay, so now I'm going to talk about supersymmetry, or more precisely, supergravity. Now, I've taught semester-long courses on supersymmetry. It's a huge subject without even getting into supergravity, which is more complicated than supersymmetry. So, and it's a subject which it's a very beautiful subject, has a lot of applications from particle phenomenology to mathematics to string theory to black holes.
And I'm not, I'm just going to talk about sort of one, but I think and actually we don't very often, I think she taught a course on it a year or two ago, but we don't very often have courses on it. And you don't even really see it in courses for the same reason that I usually sort of skirt around it, because it's a little daunting to sort of take a small taste of it. But I'm going to try to tell you just a little bit about supergravity and supersymmetry and how it's relevant. And in particular, I want to talk about a paper from 1982 by Gibbons and Hull, in which this property of black holes is explained using supersymmetry. Okay, so please feel free to ask questions if I am not, if there's some more detail that you want. So we start out in general relativity. We have one dynamical field, g mu nu. And then in Einstein-Maxwell theory, we add another one, a mu. And then in one of the simplest supersymmetric theories, we add a third field, which is a fermion, psi mu, the so-called Rorita-Schwinger field. So, the electron is a psi without a mu index. It's a Dirac spinner. This is a vector-valued spinner. And like the electron field, it's anti-commuting in nature. When you go to the quantum theory, it will obey anti-commutators, or if you try to do some rather than commutators, if you do the classical Poisson bracket, that will also be an anti-commutator rather than a commutator. Now, these fields have equations of motion. And of course, for the metric, we have the Einstein equation, which is 8 pi t mu nu. And also I mean here plus dot, 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 which, there could be more matter fields of various kinds coupled to these three basic fields here. You can also talk about supergravity without a Maxwell field, and with a psi that obeys a Majorana condition, but that's not the one we want to use to study this situation over here. So this would be the stress tensor of this thing, and of whatever else we added. So then we would also have, for A, we would have a Maxwell equation, d mu f mu nu, and there would be some current J nu well, in pure Einstein-Maxwell theory, that's 0, but if we have charged fields around, there's some non-zero current. And then finally, we need an equation for this. So this equation is epsilon mu nu rho sigma, gamma nu d rho psi sigma. And that also has some fermionic source, which we could call k sigma. Okay, now these equations have some symmetries.
And the one that I am assuming that you knew about before you started this course is the diffeomorphism symmetry of general relativity. And in that symmetry, we would have delta, it's the infinitesimal version of the symmetry, so this is diffeomorphisms, is delta epsilon g mu nu is the Lie derivative with respect, sorry, let me call it zeta. Zeta is a vector field, is Lie zeta g mu nu, delta zeta a mu is Lie zeta a mu, and delta zeta psi mu similarly will be the Lie derivative of the spinor psi mu. And these, this diffeomorphism symmetry maps solutions to solutions. That is, if you have one solution of the equations of motion, you do a diffeomorphism on it, the finite diffeomorphism generated infinitesimally by this Lie action, the new set of fields also obeys the equations of motion. Actually, there's also, of course, a gauge symmetry here, which we could also talk about, but I'll skip that. So it maps solutions to solutions. Now, there's actually a lot of subtleties, the full complexity of which has really only dawned on us, we've only really become aware of it in the last 5 years or so, of when two solutions should be regarded as equivalent. So for example, if we have a Schwarzschild black hole, we can boost it, that's a diffeomorphism, then it's moving, that's not physically the same object. It has different energy. And on the other hand, if we do some localized diffeomorphism with compact support, we probably do want to regard that as the same physical object. So there's subtleties about diffeomorphisms, when two things, when we should regard a diffeomorphism as acting trivially, taking one thing to another representation of the same thing, or whether we're taking it to a physically different thing. A fascinating question, but not one I'm going to go into now. With supersymmetry, there's an analogous set of issues about when a supersymmetry transformation takes you to something which is equivalent or is different. The supersymmetries are, so one thing that we're going to see in a moment is that some supersymmetry transformation takes the metric into psi. And so we wouldn't necessarily want to, we wouldn't always regard such things as equivalent. Now, the symmetries, so this is infinitely many symmetries. So we're just not going to worry right now about when they're equivalent and when they aren't. And the symmetry, the infinitesimal symmetry generators obey an algebra, which is that for diffeomorphism is that delta zeta prime is equal to delta of the Lie bracket of zeta with zeta prime. Okay, so the infinitesimal algebra of diffeomorphisms is just the Lie bracket algebra. And moreover, we are often interested in a special, so there's a subset of all of these things for which L zeta G is equal to L zeta A is equal to L zeta psi is equal to 0. That's a so-called killing vector. Those play a special role. We've already discussed it for Reissner-Nordstrom, the full thing. Well, for this one over there, we have only one killing symmetry, time translations. Reissner-Nordstrom, we have time translations, 3 rotations. And then in the near horizon region, we get, instead of just 4 killing vectors, we have 6 killing vectors. So we have a symmetry enhancement. Okay, any questions about that before so that's how we think about diffeomorphism, symmetry. I'm about to say something now about supersymmetry. Any questions? Yeah.
The gauge symmetry you briefly mentioned is just the gauge symmetry associated with the AU, right? It's not something about the diffeomorphism.
Right. It's another set of symmetries that this theory has, which I won't bother to discuss. Okay. So now, in supergravity, we have supersymmetry. And instead of being, so this is to be thought of as an analog of diffeomorphisms. And instead of being parametrized by a vector field zeta, we're going to parameterize by a spinner, which I'm going to call epsilon, a Dirac spinner, for 4 complex components. And the supersymmetry transformations are delta epsilon psi mu, the Rita-Schwinger field. Okay, now I'm taking a small amount of artistic license here, but really not very much. I'm not telling you anything misleading, but to say all this very carefully and define the, all the conditions on the spinners, and that it takes some time, and I'm not going to go through it. Instead I'm going to write plus dot dot dots. Plus dot dot means terms that would take a week or 2 of lectures to explain, but wouldn't affect the final argument. Okay, so delta epsilon psi mu is the covariant derivative of the spinner epsilon minus 1/4 f nu lambda gamma nu lambda gamma mu epsilon plus dot dot dot. And exactly what the dot 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 is may also depend on what the dot 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 is there and exactly what kind of matter is coupled. Yes?
What's gamma with 2?
Oh, so gamma nu lambda. So gamma is equal to a half gamma nu gamma lambda minus gamma lambda gamma nu. So gamma nu lambda is the generator of Lorentz transformations acting on spinners. Okay, and then delta epsilon g mu nu is equal to epsilon bar gamma mu psi nu plus dot dot dot. And delta epsilon, actually, I'm not even going to write down delta epsilon A because I'm not going to need it. Okay, so okay. So the first thing to notice about this, it involves a spinner. And since psi is anti-commuting, epsilon better be anti-commuting. And this symmetry transformation, so up there, the ordinary diffeomorphisms just mixes the metric with itself. Though, of course, if we think of the metric as 10 fields, a symmetric matrix, it mixes up the different components of the metric with one another. But the metric doesn't get mixed up with the gauge field or with anything else under the ordinary diffeomorphisms. Here, we're mixing up, so this, of course, involves this transformation parameter epsilon, but in here, in the covariant derivative, we have the derivatives of the metric. So this should be thought of as we're mixing up the Rorita-Schwinger field, the fermionic Rorita-Schwinger field, with derivatives of the bosonic fields. So the Rorita-Schwinger field is called a fermionic field. G and A are bosonic fields. So the Rorita-Schwinger field transforms into derivatives, to one derivative of a bosonic field. And on the other hand, the bosonic fields transform into the fermionic fields with no derivatives. Yeah, I think delta A is just epsilon bar psi nu. There are no derivatives involved with that. So supersymmetry is a symmetry transformation which mixes up fermions and bosons. And when I say it's a symmetry, it also, like that, it maps solutions to solutions. So if I have one solution of the equation of motion and I do a supersymmetry transformation on it, I get another solution of the equations of motion. Now, not every, so of course what happens in supersymmetry, of course we see that the ordinary diffeomorphisms mix up different components of G and different with one another, but don't mix G with A or with psi. But we could think of all the different components, the 10 components of G, as being in one multiplet that are related by, Lorentz transformations, for example. It's a tensor multiplet. You can think of it in supersymmetry as G, A, and psi are all part of one big multiplet. In other words, we shouldn't think of it just, we have this bigger group acting, it connects more things. So we can think of G, A, and psi as all part of one big superfield. And there are other transformations other than diffeomorphisms that act on it. There's a bigger group here, and that's the supersymmetry group. Now, of course, this structure does not appear for every covariant action. First of all, it's not true that if I take G, A, G, and A, that every action I could write down is diffeomorphism invariant. For example, if I write A3 times G74 and add that to the action, that's not diffeomorphism invariant. There's restrictions on which actions are diffeomorphism invariant. It's a principle that restricts the possible dynamics.
Similarly, it's not true that every diffeomorphism invariant or generally covariant action involving G, A, and psi is also supersymmetric. There are very specific restrictions on the couplings that you can have in there that in order for it to be true that if you do these transformations on the fields, it maps a solution to a solution. Okay, now the amazing thing that happens, so here I have the algebra of diffeomorphisms. The beautiful thing about supergravity is you can ask now, if I take not the commutator, but the anti-commutator of two supersymmetry transformations. That turns out to be the Lie derivative of, with respect to a vector field zeta, which is just epsilon bar gamma mu epsilon prime. So that is a kind of amazing mathematical fact that you could verify. You have to write it out in a little more detail, that if you, in fact, iterate, I mean, you have to write down A and actually maybe not to just get the transformation on the metric. So if we take, you see, if we take delta epsilon G mu nu and we get this, then we vary this again, we get a derivative on the epsilon, and then we take the anti-commutator of it, we're going to get some, it's clear to see that you'll get something on the right-hand side. In other words, if we take this, take the commutator of these two actions here, we'll get something on the right-hand side that has an epsilon and epsilon prime in derivative of the metric. And it's some amount of work and actually a very beautiful thing that works out to be exactly the standard Lie derivative transformation rule. So one could say here, and it's often been said, now there's another term here I'm going to talk about. One could say here that in some sense the local, these are called local supersymmetry transformations. There's also, when you hear people talking about supersymmetry, especially in particle physics, they're often talking about global supersymmetry. So let me just say a word about that. So in quantum field theory, we have, the 10 Poincare transformations, translations, boosts, and rotations. And those are global symmetries. They preserve the vacuum. For each one of them, there's a killing vector, which is a killing vector for the Minkowski metric. And that in general relativity, general relativity, that sort of those 10, of course, the Poincare transformations are coordinate transformations, very special coordinate transformations. Those 10 coordinate transformations get enhanced to infinitely many in general relativity. And similarly, here I'm going straight to the infinitely many version, which is what we're going to need. But in particle physics, there's a truncation of this where there would just be 8 spinners that would be allowed, constant Dirac spinners. They have 8 real components. And they would obey an algebra that actually they would the way you would usually do it, they would just square just to the translations. And so anyway, so that's what global symmetry is, when you just talk about that smaller group with constant epsilons and flat space. Here we're worried about local symmetry, supersymmetry. Global supersymmetry just isn't even defined in a general curved space-time. So one often hears the statement that supergravity is the square root of general relativity. In other words, you square a supersymmetry. Local supersymmetry transformations are the square roots of diffeomorphisms. You square them to get ordinary diffeomorphisms. And it's a very weird and surprising thing that there's some sense in which general relativity has a square root. And that accounts for many of its kind of otherwise seemingly magical properties. Now, any questions? Oh, yeah. So there's one more term here in general, which is allowed just by algebraic conditions. It's called the central charge Z. And it has to commute with everything. Just for the algebra to close, it has to commute with the supersymmetry transformations and the coordinate transformations. And this is the central charge. And in the context we're interested in now, this central charge is, roughly speaking, epsilon bar epsilon times, it's going to become epsilon bar epsilon times the charge Q of the, when we get to Reissner-Nordstrom, that's going to become the total charge Q, which is a constant which commutes with everything. And that's going to be important in understanding where this Bogomolny bound comes from. Okay, so here we had killing vectors. Actually, let's take a. Let's take our 5-minute break now. But let me pose a riddle. So if we have killing vectors, are special kind of vector fields in a diffeomorphism invariant theory, and they're defined by this condition, what is the analog in a supergravity theory? In other words, what should we call a killing spinner? All right, but let's take a 5-minute break. Okay, so maybe I'll go over here. So the analog of a killing vector, yes? Zero. There's a lot of different, in general, it has to be something that commutes with all the other elements of the algebra. But if it's an asymptotically flat spacetime in this theory, it can only be, Q is the only the only game in town. The only thing it can be.
Does that mean that the central charge is zero, or is there some expression?
The central charge would be 0, yeah. Okay, so instead of a killing vector, we now have a killing spinner, and we define it in exactly the same way that we would say a killing spinner epsilon, let's call it epsilon naught, a particular spinner. So these formulas were over here are true for any spinner, for any Dirac spinner. Just as these are true for any vector field zeta. Particular vector fields, I could have put a 0 up there, we would have all of these conditions. And more if there are more fields in the theory. Now, so just as in the study of just general relativity, spacetimes with killing vectors are of special interest, in the study of supergravity, spacetimes with killing spinners are of special interest for reasons which for many reasons, which you'll see shortly. But usually, we're interested, so to specify a solution in a supergravity theory, we have to specify all these things. And generally, or often, in fact, almost always, one considers solutions in which the Rita-Schwinger field and all the fermions are just 0. And there is some discussion of, especially when you're talking about supersymmetry breaking and so on, of contexts in which these things should be non-zero. But for most applications, we'd be considering solutions in which the spinner fields would be 0. So this last equation then becomes trivial because psi is 0, and by statistics, the right-hand side has to include at least one fermion field. And so if all the fermions are 0, this last equation becomes trivial. And indeed, what we're interested in the moment is a theory in which reduces to Maxwell-Einstein theory when all the fermion fields are turned off. So since these variations are linear in the fermion fields, if we're talking about solutions where this is 0, again, you're free to talk about ones where this is non-zero, but most of the interesting things that have been learned have been from the case where these are 0. Then these variations vanish trivially. These equations become trivial because they're odd in the number of fermion fields on the right-hand side. You see, if psi is 0, this right-hand side will vanish no matter what epsilon is. So that doesn't give us any constraint on epsilon. We want a constraint on epsilon, which is the analog of the killing vector constraint on zeta. And so that entire constraint just comes from this, which is equal to d mu of epsilon naught minus a quarter f mu nu, f mu lambda, gamma mu lambda, nu lambda, gamma nu lambda, gamma mu epsilon. Okay, now this equation is a spinner, and it's got a free index.
And so so epsilon, we should think of this as an equation. If we're given, it depends on F and the metric, the gauge field and the metric. So given the gauge field and the metric, we have here 8 times 4, because Dirac spinors have 8 real components. We have 8 times 4, which is 32 equations, first order linear differential equations, 32 equations for 8 real epsilons. Usually you can't satisfy, usually you won't be able to find, usually you want to have the same number of unknowns as equations. And we have 4 times as many equations as unknowns. So this equation will have solutions only for under very special situations. Also true of the Killing vector equation, right? So Killing vector equation, it's a symmetric 4 by 4 tensor. So that's 10 equations for the 4 components of the vector field. In a generic background metric, there are no solutions to that. Only very special solutions like Schwarzschild or Reissner-Nordstrom do you have solutions. So when does this solution have an equation? Only for special backgrounds. And so we're in this week's homework. I want you to show that in this background here, recall that, let's see if I erase that. So we had ds squared is 1 over v squared minus 1 over v squared dt squared plus v squared dx squared. And in this background, it turns out that epsilon naught of the form v to the p times some constant epsilon with some conditions on it. Let me put here. So the homework problem is to find the epsilon naught, and I'll give you a hint that it looks something like this, which solves this equation. Okay, I'm not going to do this on the board, homework problem. So this is a very special space-time. It has, in addition to the one killing vector, it has only one killing vector, but it has extra killing spinors. So the words that we would use to describe this is that it's a supersymmetric space-time. It's space-time with some extra supersymmetry in it. Now, when we look down at the bottom of these throats, we have ADS2 cross S2. And ADS2 cross S2, and that corresponds to an SL2R times SO3 isometry group. But not only is there enhanced bosonic symmetries down here, I guess I'm not assigning this as a problem, but you could work it out if you wanted to. There are also enhanced supersymmetries down here. So if you just look at the Robinson-Bertotti universe and ask how many supersymmetries there are,
in other words, spinor fields that obey this equation, it's twice as many as in this full extreme Reissner-Nordstrom geometry. And by the way, for the non-extreme, when m is greater than q, there aren't any supersymmetries. It's only when it's extreme that there are any solutions of this equation at all. Let me just say one more thing. So now we have these extra supersymmetries, and we have a group that acts on this. So if we look at the whole space-time, including the asymptotically flat region, before we started thinking about supersymmetries, we had a symmetry group. It was just a abelian group of time translations, pretty simple one. If we just had one Reissner-Nordstrom, we would also have the rotations, 3 more rotations, the rotation group. But just for the multi, we had this just abelian group. And then we get more supersymmetries. So we get a supergroup. In other words, we get some supersymmetry transformations whose squares contain this time translation. Okay, and just as the group of time translations down at the bottom of these throats, you go from 1 in the multi-Reissner-Nordstrom solution to 6 in the near horizon solution, just as you get an enhancement of bosonic symmetries leading to a larger isometry group, you also get an enhancement of supersymmetries leading to a larger supersymmetry group. And there's a whole story of classifications of supersymmetry groups and their representations and so on, which is a very rich story, but I'm not going to go into that now. What was your question?
I was wondering if there was, so as soon as you go even a little bit away from extremality, all of the supersymmetry breaks. Is there any developed notion of some way to do perturbation theory or to get something like non-trivial about the slightly non-extremal cases of these Nordstrom geometries from the supersymmetries? Like usually when you have symmetry in a problem and you vary a parameter a little bit, I can still use some remnant of that symmetry to say something new and non-trivial.
Right. That's also going to be one of the homework problems. There's a limit in which you can be very near. And though I don't, right, there's a limit in which you can be very near the fixed point. You could have asked that question before. Your question was logically independent of supersymmetry, right? You could have asked, suppose it's not quite extreme. Does this enhanced group tell us something?
Sure.
And the answer is yes. There's a whole interesting structure there, and then it gets even richer when you include the supersymmetry.
You referred to you said like bosonic symmetries when you were referring to like the killing vector symmetries.
Yeah. So people wouldn't usually add the adjective bosonic because before the fermionic symmetries came along, they were the only game in town. So you didn't need an adjective to distinguish them. I only add the adjective bosonic when I'm about to talk about fermionic symmetries in the next sentence.
And I suppose this is because one's a 4-vector, one's a spinor object.
Yeah.
Is there? I know that there's when you have like there's some sense like there was Weinberg's classification or whatever when you get like irreducible representations of symmetries can be considered or like how you get particles in some sense. Is there any is there anything deeper to that language than just one's a vector, one's a spinor? Is there any relationship to like actual physical fermions and bosons with these killing vectors or spinors?
Well, Of course, you have multiplets of the things that transform in the Poincare group and the Weinberg. I'm not sure which reference you're referring to, but certainly that's, Wigner or what, Oh, you meant Wigner. Yeah. A little before Weinberg. There's also a very rich story of supersymmetry multiplets, and of course it was the great unfulfilled hope of much of particle physics that that the world that the particles we observe in nature are part of super. I mean, it could be true, but there was a hope that there was a very concrete hope about how we might actually have seen that at the Large Hadron Collider. Not everybody has given up on that hope. I think a lot of people, there's something so compelling about it. I mean, in my own mind, the status of it, and maybe I'm not that far from what the typical physicist is, that it's so nice, it's tempting to believe there's some truth in it, but it's unlikely that that would be experimentally realized in the in the foreseeable future. But some people think the next round of the LHC or the next collider will see it. It's not impossible or silly, but yeah. More questions? Okay, so now, okay, so we get not just enhanced bosonic symmetries, but enhanced supergroups in these near horizon limits. And now let me say something about what does that have to do with this seemingly miraculous thing that m is equal to q. Okay, so let's suppose that there aren't any charges around. We're just talking about, I think I don't need this. Well, maybe I'll leave it anyway. Where am I over here? Let's think about just q equals 0, and let's also take a mu equals 0. Then we can effectively ignore that term, and we have delta epsilon prime, anti-commutator, is equal to the Lie derivative of zeta equal to epsilon bar gamma mu epsilon prime. Now, there exists epsilon such that, or epsilon, I could take epsilon equal to epsilon prime, such that epsilon bar gamma mu epsilon d mu is equal to d by dt. At least, we could do this globally if we have a definition of t, but what we really care is what happens for r going to infinity.
So in other words, I can find a supersymmetry transformation, which is the square root of a time translation. So a time translation, a time translation, so then this becomes a time translation for that epsilon. Let me call it epsilon t, epsilon t, epsilon t, epsilon t, epsilon t. So this will just be equal to 2 delta epsilon t squared. So that this is related to a Hamiltonian. H this action d by dt is generated either in a classical theory via Poisson brackets. We're sort of more used to thinking in quantum terms of we have a state and Hamiltonian acts on a state and its eigenvalue is the energy. But the discussion I'm having, we can talk about it purely in terms of classical mechanics, where we have some Hamiltonian, which is a function on the phase space, and Poisson brackets on the phase space of any field on the phase space, with the Hamiltonian generates time evolution. The quantum language is, I find, simpler than the classical language, but okay, it amounts to the same thing. And the classical story is the limit of the quantum one. Here, we have some, let's call it, what do I want to call it? It's usually called Q, but I don't want to confuse it with the other Q. Let me write it like that. Okay, sorry. What should I write it? Let me write it Q epsilon. So each one of these is a Q epsilon. So I have a relation of the form Q epsilon squared is equal to H. So in other words, the Hamiltonian in supergravity has a square root. There's an operator, and one can show it's a Hermitian operator whose square is the Hamiltonian. Okay, now one of the outstanding problems in general relativity was to show that the energy of any asymptotically flat solution of general relativity is always positive. And that was a conjecture that was made by Arnold, Deser, and Misner in the 50s, or even more before. I mean, I was probably clear already, in the 20s that there better be some way to define energy in general relativity and some limit in the far field limit, and it better always be positive. Because if the energy can get negative, then you can perturb the vacuum into one clump with negative energy and one clump with positive energy, and the phase space for that would be huge, and everything would just explode immediately. So very important that the energy be positive in general relativity, but an extremely inobvious feature of the field equations. And the importance of this problem began to be understood, starting in the 50s and so on. And finally, Yao, who he told us a little bit about this, one of his most famous works, he proved in the early 70s, using very advanced methods of differential geometry and minimal surfaces and so on, that the energy is indeed already positive, always positive. Rigorous theorem in general relativity. You take any initial data slice that is asymptotically flat, you have to solve the so-called constraint equations on that slice, or maybe put another way, we take any solution of the Einstein equation that's asymptotically flat, we look at that slice and we take the energy associated with that slice, and it's always positive.
Okay, then I think it was Deser and Grizzaro, who were some of the discoverers, the early pioneers of supergravity, looked at this equation and said, hey, the energy in general relativity is the square of something. Therefore, it has to be positive because of supersymmetry. In other words, just the mere fact that general relativity has an extension to a theory with supersymmetry says that it has to be positive. Now, they made this statement at some seminars. I think there was some paper that said it or something. But it all seemed very kind of formal. These are operators in some quantum theory of gravity. Who knows what that really means? And this is not a sort of rigorous mathematical proof of anything. But then in the early 80s, Witten took the intuition behind that, sort of threw away all the quantum stuff, turned this into some equation, showed that indeed you can take this variation of the metric and you can actually construct you take some spinor epsilon and you can actually write the energy as an integral over a spatial slice of something, roughly speaking. It has the form, the gradient of epsilon squared, all covariant. So we just have to have a spinor who asymptotically obeys this. And you have a gradient of epsilon squared plus something that looks like T mu nu Yeah, I think it's plus T mu nu and mu, where n is the normal to the slice, epsilon bar gamma nu epsilon. Any solution of the Einstein equation, even with matter in it, you can write the energy in this form. And you can do that sort of following your nose from the supersymmetry structure. Now, this has the property that this term is positive, and this term is positive as long as the matter stress energy obeys a positive energy condition. Of course, you could never hope to prove a positive energy theorem. So Yau's proof of positive energy theorem didn't just apply to pure general relativity. It applied to general relativity coupled to matter whenever the whose stress energy tensor obeys T mu nu L mu L nu is greater than or equal to 0 for L in the a forward directed a directed that lies in the future light cone. So that's basically some covariant version of the energy is positive. And so the energy has to be positive. You have to assume that. And the matter energy density is positive. You have to assume that. And then if you assume that, then this you have this expression for E consisting of two terms which are both positive. So this kind of vague intuition that Deser and Grizzaro have, that in supersymmetry energy has a square root, and its square root exists as a well-defined quantity, has been turned into, with some work, a rigorous mathematical proof that satisfies real mathematicians that that the energy in general relativity is always positive. And by the way, it's to a mathematician, it was a very weird way of proving the theorem. It's not something they would ever have thought of, and it came from this supersymmetry structure.
Now, we get a little more than the fact that this is positive, that the energy is positive. So this implies that E is greater than or equal to 0. But in order for it to be 0, we need both of these terms to vanish since they're separately positive. So we need T mu nu to be 0. And we need grad epsilon to be 0. Now, I haven't spelled out all the details of the structure of this grad epsilon squared and so on. But it basically, now we've set A to 0, it basically amounts to the statement that there's a covariantly constant spinner. So in order for, so you can show that in order for this expression, for the inequality to be saturated, you must have a covariantly constant spinner. And that's true in flat space. And indeed, in flat space, there are 8 killing spinners, any constant spinner. So this equation, when I set A to 0, and I'm in flat space, this becomes just an ordinary gradient of epsilon is equal to 0. It's obvious that any one of the 8 real epsilons will satisfy that. So we have a covariantly constant spinner. T is also 0. These two terms both vanishes. So the statement is that so for Q equals A equals 0, E is greater than or equal to 0 with E equals 0 if and only if there exists epsilon naught such that d mu epsilon, I'm dropping this term right now, d mu epsilon naught is equal to 0, which implies flat space. Well, let's see. If we're talking about asymptotically flat, a little hard for me to answer your question, because you're talking about asymptotic, what we are talking about here, asymptotically flat solutions of the vacuum Einstein equation. No electromagnetic field. The only such solution is flat space. So there aren't ones with more, if they have any killing spinners, they have 8. There aren't any with, there are some with other numbers of supersymmetries, but they're not asymptotically flat. So in the category we're discussing now, that would be true. More generally, lots of other interesting things can happen, and you might have, it might be something related to a null vector or something like that. You can have, half flat things, PP waves. There's all kinds of interesting things that can happen here, but I'm right now just talking about asymptotically flat solutions. And you get all kinds of other interesting bounds. Okay, so now let's take Q not equal to 0. So this is an example of what's called a Bulgamoni bound. And Bulgamoni proved his Bulgam bound using a very different kind of method. But now a lot of things called Bulgamoni bounds are proven using supersymmetry.
So the statement is that something has to be above some value, it's bounded from below by something, and something special happens when the bound gets saturated. So when Q is not equal to 0, we have that this reduces to, so here we had Q epsilon squared equals H. But now we get a minus the charge here. Okay, so instead of learning that the energy, so the energy minus, so this Q is not this Q. This is the electric charge of the black hole. Or in the multi-Reissner-Nordstrom, the Majumdar-Popetru metrics, it's the sum of all the charges. We learn that the difference between the energy and the charge is the square of something, therefore positive. So we learn that the energy is greater than or equal to charge. And it can be equal to the charge when this Q epsilon is somehow 0. And the Q epsilon being 0 is the same as the statement that the Q epsilon annihilating the state is the classical version of that statement is that the Rurita-Schwinger field is left invariant by the associated supersymmetry transformation. So we have E epsilon greater than or equal to Q, and epsilon equals Q if and only if there exists an epsilon naught such that now we have to put in the extra piece, d mu epsilon naught minus a quarter f alpha beta gamma alpha beta gamma mu epsilon naught equals 0, which now is not just flat space, but this condition has more solutions. It implies not flat space, but the Popetru-Majumdar metrics. So these Popetru-Majumdar metrics are supersymmetric. They saturate this bound, and that's why there's no forces between the black holes. If there were a force between the black holes, that would mean that there would be a linear change in the energy of the configuration if you moved them either closer or further. And so by moving them either closer or further, you could make the energy less than the charge, thereby by violating the bounds. So the bound is preventing this bound is preventing them from there being any force between the black holes. And this was again this very kind of naive statement was made into a rigorous mathematical proof by Gibbons and Hall in 1982, shortly after Witten's paper, and that was also the first paper, I believe, to point out that these spacetimes were supersymmetric. So right. So I guess this was a huge amount to absorb in one lecture, but what do I want you to take away? Well, general relativity has an extension to a theory which has a lot more symmetry, supergravity. And that the possibility of embedding general relativity, the fact that general relativity can be embedded in the supersymmetric theory, mandates that it have a lot of special properties, like these solutions where there are no forces between the black holes. Also, the enhancement of symmetry in these near horizon regions, the positive energy theorem, and again, symmetry reasoning based on supersymmetry often gets used to try to understand properties of black holes. So I thought I should at least say a few words about it without teaching a whole course. So, any questions? Okay, great.